Here. Okay. Okay, thanks very much for the intro. What I want to do today is talk about hardware testing, which is for AWU maybe a little bit unusual, but I think actually it's interesting for the audience possibly to have a look a little bit at the behind the scenes and to give you some idea about what's happening there. And if you got more questions, please feel free to approach me. So this is going to be very, very high level, a few things. Okay, so why do I feel qualified to talk about this? I work for TriOptics, which is basically an optical test company, optical test and manufacturing company from northern Germany. We are part of the Jenoptik group. The company itself was founded in about 30 years ago, and we basically work in all kinds of optics testing. So we work from a smartphone world, we work in medical optics, aerospace optics, basically a very wide range. And one of the big topics that we work on is the AR/VR world. We are basically have subsidiaries worldwide. We work in mass production all in Asia. We work in R&D worldwide. That's kind of we have 500 employees at the moment. So what do I do? My job is currently to basically look at all the new technologies that are happening in the AR/VR world and also think about how can we test those, what do we need to do, how can we help our customers, which are mostly the hardware companies, to basically come up with better quality headsets for new technologies. Okay, so let's get started. As a kind of a motivation, I want you to look at this picture and imagine it's 3D. So you're like a mechanical designer, you're designing a new nice looking instrument, and you have it in front, you put your VR glasses or MR glasses on, you see it in front of you, and that's actually what you would like to see. So you want basically a sharp, crisp image, you want to be able to read all the text, and that's the ideal what we actually want to have from AR, VR, MR, XR, whatever you call it, hardware, basically something that really looks lifelike. The reality looks a little different. It will probably look more like this. So you got all kinds of artifacts in there. So you got tint there, you got the contrast might be not as good, there might be inhomogeneities in brightness and so on. And what we do is basically, if I want to throw a few parameters on here, basically what our business is, we measure this, give our customers who are the actual hardware developers or the people who actually do the mass production of these devices, the data they need to basically build better products. And these are kind of, for example, some of the measurement parameters that you would typically get for such a system. For example, you look at the contrast. What is the contrast? Can I read? Is the contrast high enough that I can actually read text if I have a virtual screen in front of me? Is it bright enough? These are the things that we typically work with, and we work with our customers during the R&D phase when they come up with new designs, but also in the mass production phase when they actually want to have high quality, high yield, large number kind of products, and they need to test in many steps on the way to basically get what you can actually buy at the end when you take out of the box, and hopefully it's a very good quality. So what do we actually test? So this is just a sketch for a see-through AR type display. So what will be tested on this? Obviously, we don't want to test at the end because that would be a problem because we would need to throw away a lot of the finished headsets at the end. So we want to test on many different stages in between to make sure we only use good components as we go to the next step and integrate them. So the first thing is display test. Next thing would be actually the actual projector, like there would be the lens test. If we put the lens and display together, we get our light engine that we would test. We have typically in such a system a combiner that could be a waveguide, for example, like the one that Pia from Dispelix just talked about. This would be a typical waveguide combiner here. We might have prescription on there, so we want to test this as well. We test the whole system, the whole near-eye display, which is like projector plus wafer plus combiner. as a whole system. Then we actually take two of these and typically put them together and need to make sure they're correctly aligned, because if there's a lot of misalignment, people get headache. Turns out it's super important. But there's not only the optical system that is like the display, but we also have all these sensors that are there. And that could be, for example, your eye tracking cameras. That could be your machine vision cameras, your color cameras on the outside. So there's a lot of sensors involved as well that are being tested on the sensor level, on the optics level, on the module level. And they also need to be put together and aligned in the system. So there's a lot going on. Okay, so typically I said, like, we do this in different stages. We don't test at the end because the yields would be way too low. So typically what we do is we have a component like a lens. Some manufacturer will produce the lens. They will test it because they test it before it goes out to make sure that the quality is okay. Then this lens will basically go to another company in most cases who will integrate it, for example, with some other components. And I'm showing here, sorry, I forgot about this. This is basically a VR headset kind of view. So we have this is sort of like the objective. We add a display, we get a near eye display. Basically, they can put in front of you. You got two of those displays. You add cameras and sensors, and in the end, you got a headset. So where is the test happening typically? So typically, after each of those steps, there is going to be a test. There could be many more, but that's the minimum amount what's required. So we make sure the quality is okay. And there's typically another thing that we call here like alignment. So basically, things need to be put together. That's another step that is being done in many cases, and it's also where we work quite a bit. So this basically are our two business sides, like the testing and the alignment. So there's many steps, many different locations. Typically, all need to be done in order to get the quality at the end. Okay, so what do we test? In principle, from the top down, we look for material parameters. This is an optical system, so materials are super important. I will basically show you just very briefly like one example of what is being done in material testing. The next thing that I will also only very briefly touch is optomechanical parameters. And that's, for example, when you have a lens system. So for basic lens, you want to know what is the radius of curvature. What is the centration? How well is it basically the optical axis aligned with the mechanical axis and things like that? Or for waveguide, for example, how flat it is, how the glass wafer, how thick it is, what the air gap is and stuff like that. So we'll only touch a little bit about this. So this is very important because errors here in the actual shape, for example, or how things are being put together, typically end up being in a lower image quality. And that's the next step that we're going to do, is we're going to test image quality. And image quality means mostly like if I put this in front of an eye, how does it perform? Is it bright? Is it in focus? Things like that. So this is going to be a big part. And last but not least, I talked about this. This is kind of like the alignment part, where we say like, are the things put together correctly? So this is basically the four things that are sort of like the categories that are being tested. And as we go from components to systems, typically it goes like this. So the material obviously is only interesting for components. Also how they're put together, what is the mechanical properties. And as we go more and more into the final headset at the end, it's going to be a lot of image quality testing and alignment testing. These first two I'm going to touch only briefly. I will spend a bit more time on this and a bit more time on this. Okay, let's talk about material parameters. Just one little example here, maybe to not dive too much into it, but the material parameters are sort of like the base of the performance of an optical device. That could be a lens, for example. You need to know one of the most important ones is the refractive index. It's just a physical property, basically how much the light is being diffracted. Refractive index. So this is one of the most important parameters from a material point of view. And this is something that people do in the whole of optics. It's not AR/VR specific, but I just want to show you here a little like a little machine. Actually, how would you test a refractive index? Actually, by doing angle measurements. So basically, you've got a prism here. You know the shape of the prism. You basically put in light with a known wavelength, and you basically measure extremely precisely what the refraction is basically on that prism. And you can do this with basically an accuracy of about a part per million. So we're talking about, if we talk about refractive index of 2, then it's more like we can measure it to 2.00000x. So that's kind of like the precision that you're looking for in this business. Okay, next example, I said I only want to very quickly go through it, is optomechanical parameters. We could talk for hours about this. The example I want to show you here is pancake lenses. So you all know like the newer generation of VR or camera-based pass-through MR headsets. They're going to use pancake lenses. So what we have here is basically, sorry, wrong here. So we got several lenses that are being put together. There's polarization elements, so it's a really complicated design that basically bounces the light back and forth several times. So it's a complicated lens. We have the display here very, very closely to it. The display is being projected to some infinity or some virtual distance that the eye can focus on by this lens. And in order to get decent image quality for this one, it's very important that, for example, the lenses, the polarization elements, they're all like aligned perfectly. So if they're a little bit tilted, suddenly you get ghost images. So you get like basically the same image several times. And this happens because the light is being bounced back and forth in the wrong way. And that can be really just a slight misalignment, and it will create like a very bad image quality. So what we do here is we, for example, look at the shape here. These are all A-spheres typically, so they are not non-spherical, so you need to measure the shape. You need to know what is the orientation of the shape regarding to the mechanic, like the actual sides, for example, or what is the orientation of this shape here to the other side. And there's a whole lot of instruments that are being used to test for this. Next thing is image quality. So I said like image quality is one of the big things that are kind of like evident for everybody who's actually putting the headset on. The conventional way to do this is basically using a camera system, like the same you would do for like a big LCD TV. You basically have high resolution cameras. You look at the image that you get, and in a similar fashion, because obviously it's a different imaging distance, but that's what most people use really is kind of, and I didn't put our competitor's picture in here, so this is a sketch for it. It's basically a camera with a big objective, and they look at test patterns. Basically checkerboard patterns where you say like, okay, what is the brightness difference here? What is the contrast between those? How homogeneous it is? So this is kind of like the conventional way of testing image quality for near-eye displays. We believe that this works quite well for kind of like what we have right now, but with the actually increasing quality that we get, we think you need a lot more information. And that's why we have a very different approach, where we have quite a bit more complicated systems. So basically, typically what we have in these systems is we test a lens in this example here. So this is the lens we test. This could be a VR lens. What we do is we send something into the system that we know. So a test pattern with a quite complicated optical system. So this is for a lens here. If it's a headset, obviously we don't need to do this. So we project something, and then we look with another box here, which might look like this or very different. Basically look at what the human eye sees on the other side. And because we know what we put in, we see basically what we get out. We can actually derive a lot of these parameters. For example, I want to show you here, without going too much into detail, this here is, for example, something that you wouldn't be able to do with the other system. we have here the display. So the display is somewhere like that black line here. And this is our lens here. And we want to know, or what we want to show is like, okay, if I shift my focus, my display a little bit out of focus, how does my image, my contrast in this case, so this is contrast shown basically going to change. And you see it's a quite complicated picture here. And lenses, for example, they typically don't have a flat image plane like you would like it to, so it's slightly bent, so like the one you see here. So basically, with all this information, we can find out what is the best focus plane in there, where I not only have like a sharp focus in the middle, but also like on the edge. And this is always trade-off. So you can see, for example, it's like when I in manufacturing, what is my depth of focus on this side here? How much accuracy do I need to actually put things in the right location? How do I get to that data? Just a very briefly thing again. So I said already, we're going to do basically measurements. We send in something we know. That could be something really simple, like this cross pattern here. We detect it on the other side where the eye is. And then we look at parameters like what is the line shape, where is the actual cross that we look at, what is the brightness, and so on. We calculate values out there. For example, this is a contrast function that we get from this cross. And we do this typically not in one location where we just say like look straight and basically in one eye box location, but we basically look all around in different eye box locations and so on. And then we can get basically aggregate the data and get actually the data that you want to know. So this is, for example, for a diffractive waveguide here, how the contrast for a certain feature size basically changes as you move your eye around in the eye box, and you see it's not symmetric, it's not homogeneous. So this is basically data that we get here. I need to speed up a bit, I guess. Why is this interesting? For example, it gives you an idea like, can I actually read text on my virtual screen in the end? I need to have a system that can resolve small text, and all these basically these contrast values give you a benchmark and say like, can I do this or not? Last thing, very briefly, talking about not only basically image quality in that sense that we look at optical parameters of lenses, but we also look at optomechanical parameters for image quality. So we had that Dispelix talk before. So this is basically about waveguides here. Many of these are typically stacked. It's not just one waveguide, it's actually 2 or 3 waveguides stacked together. And it turns out it's very important to make sure that these are perfectly oriented to each other. And we've got technology, for example, these are measurements for different surfaces here. So these are that are in a waveguide. It's a little exaggerated here. But we can tell you exactly, you put it together, your waveguide stack, and then we can basically non-destructively, optically only measure all the insides. Basically, we know how the surfaces inside look like. And why is this important? If they are basically not aligned perfectly, it means that your different colors, like red, green, and blue, will actually have a different angle. So if you want to do a white pixel where you combine red, green, and blue, and they are not perfectly aligned to each other, like down here, you will get something like this. And this is due to misalignment of the waveguides. Okay, I'm going very quickly through here. If you've got any questions, please free to ask questions afterwards, or we also got a booth, so I'm happy to answer these in more detail. The last thing I want to talk about is active alignment technology. So far we talked about basically testing, but it turns out actually that this is very useful to have this test data. Is also very useful to put things together in the correct way. Because if you have 2 parts that go together, you could either stick them together and say like, and hope it will be okay, and you can measure, of course, the quality afterwards and say like, okay, it's good or not, but it turns out the yields are not very good in this case. It would be much better if we actually test the 2 together and then figure out how we can assemble them together to get the best quality you can get out of these parts, and that's what we do here. So basically use measurement data to drive assembly processes. And these get quite complicated. So this is not an ARV, it's a camera assembly setup where we put sensor and optics together. There's many different ways, many different problems. I just want to give you in 2 minutes just an idea about a possible principle. For example, aligning like a VR lens with a display. And in the ideal world, you basically have the display and you want to know where do I have to put my display in order to get the best focus, a sharp image all over the place. So if you move your display up and down and look at the contrast, which is this value here, that at some point you will basically, if you're in the right location, you will get a sharp image. So that's basically my focus point. So this is the ideal case. In reality, things are a little different because your lenses are not perfect. There's not like the mechanical housing is not perfectly aligned to the actual image plane. So what you have instead is like if you do this and go up and down, suddenly you will have basically a sharp image in one corner. Then as you move around, this is basically this one curve, you get a sharp image in the middle, and then you get a sharp image on the other side. But it's never sharp at all times. So what we do here is we basically, in our systems, would measure this, basically measure these curves, and then based on these, figure out what is the best orientation of the lens, or in that case, what is the best orientation of the display in order to make this work. And it turns out if you tilt the lens in a certain way, you basically be able to get a sharp focus all over the place. And this is like one example of the things. We do it in the principle, we do it in many different cases. Light engines to waveguides, all these things, but it's always basically using data to assemble things in the best possible way. Okay, that was my whirlwind tour through testing. As said, please feel free to ask questions. What I wanted to show you today is just give you an idea about that. There's a lot of testing going on in the hardware side before you actually take that headset out of your box. It's quite important to get basically the quality up in R&D, get the prices, the yields, basically a low price for that because the yields are good. I wanted to show you that not only it's like testing, but it's also we can use the testing for assembly work. And that's the fun part for me, is basically there's a lot of innovation going on in the space. There's a lot of new display technologies. So we need to basically reinvent ourselves all the time to work with our customers to keep up with the times and give them basically the tools they need to get the best quality out of their products. So thanks very much for your attention.
Thank you very much, Daniel Winters. This was very interesting. And let's see if you have any questions from the audience. We have now the chance to ask it. I guess we have one question, time for one question. Here we go. Please say your name and what you do. I will hold you the microphone.
Thank you. I'm Luhab Nouia from Trilight Technologies. I'm the optical architect. I have one question regarding the testing. Do you have equipment specifically designed for augmented reality displays, or is it multiple instruments that you use for testing that?
We have, as we said, like we do quite a bit of technology, like in the smartphone space, for example. So if you look at some of these components, we will use our standard products that we had for a long time. But for a lot of these, basically, we have dedicated products. For example, for waveguide testing, for near-eye display testing. For example, if you look at VR lenses, the pancakes, there's like polarization happening now. It's not a conventional lens anymore. So we basically have to continuously develop new technologies, measurement technologies, in order to basically be able to measure these systems. So that's the really fun part of my job.
And one quick question. Here, yeah.
Yeah, my name is Stefan. I'm from Germany, and we're creating VR experiences in the safety industry. And I just want to ask you if it is really possible to create a better lens only by analyzing the data you create on your testing, or is it more or less at the end a try and error, even though you have those data, the testing data?
I think it's with everybody who's involved in the process will tell you that testing is the thing that moves you forward, because it gives you an idea if you're improving. Yeah. Of course, you might come up with a new idea, like I could do, I don't know, use liquid crystal varifocal lenses. You still need to do a lot of development but it helps you basically speed that up instead of like blindly trying things and say like, oh, this worked maybe, or maybe like, okay, the lab technician says it's better than the old one, but maybe it's a different day, it's not better, so you want hard data, and that helps you like iterate faster. That's basically what we do.
Thank you.
Mm-hmm.
Thank you very much. And this was Daniel Winters, Senior Technical Expert, Optical Testing at TriOptics. Thank you very much.
Thank you.